In my earlier video, I have discussed about construction of group and their subgroup, their number of elements with Sylow's theorem. And today I will discuss this construction more deeply. But at first I will recommend you, please see my earlier video. Then today's video would be so easy. Consider a group of order 6 which is equal to 3 times 2. Since 2 divides 6 but 2 square does not divide 6, so as proceed before, we can tell there exists a subgroup of order 2 which is 2 SSC, 2 Sylow subgroup. Also we can apply here Cauchy's theorem. Since 2 is a prime number, so by Cauchy's theorem we can tell there exists an element of order 2. Consider this element x which generate always a subgroup of order 2. Consider this subgroup as S and consider order of this subgroup is 2. Okay. Now similarly, by Sylow's theorem, since 3 divides 6 but 3 square does not divide 6, that means by Sylow's theorem there exists a subgroup which is 3 Sylow subgroup. And similarly, since 3 is a prime number and 3 divides 6, so by Cauchy's theorem we can also tell there exists an element of order 3. Consider y be an element of order 3 which always generate a subgroup. Consider this subgroup K, and this is the, by Sylow's theorem, this is the 3 SSG and order of this subgroup is 3. Okay. That means this subgroup contain the element 1, y and y inverse. And since 2 and 3 are both prime number, so A's and K both subgroup would be normal in G. All of us know it. If we consider the relation x, y, x inverse, since K is normal, that means this element x, y, x inverse must be belong to this part because K is normal. We all of us know it. Okay. One cannot possible. That means there exists only two possibility, either y or y inverse. And if x, y, x inverse equal to y inverse, and notice there exists an element x of order 2 and there exists an element y of order 3, and x, y, x inverse equal to y inverse. And recall the structure of dihedral group. This structure is similar to D3 group. Then this group of order 6, if x, y, x inverse equal to y inverse, then this will be, G will be isomorphic to D3. Okay? Well. And if x, y, x inverse equal to y, then x and y both commute to each other. In this case, G is isomorphic to cyclic subgroup generated by x, direct product cyclic subgroup generated by y. Let's see the proof. Consider there exists a mapping from cyclic subgroup generated by x, direct product cyclic subgroup generated by y to G, and consider this mapping as phi. This map is look like x to the power a comma y to the power b goes to x to the power a times y to the power b, where for all ab belongs to integer. For isomorphism, at first we have to prove homeomorphism. We all of us know. Notice one thing, since cyclic subgroup generated by x and cyclic subgroup generated by y is prime to each other, then their intersection always will be 1. for all AB belongs to integer, if we consider this relation x to the power a times y to the power b times x to the power minus a times y to the power minus b, if we consider this part, this bracket, since we all of us know the cyclic subgroup generated by x is a normal subgroup, that means this part belongs to cyclic subgroup generated by x, this is also belongs to cyclic subgroup generated by x, that means this part always be member of cyclic subgroup generated by x if we consider this bracket. Now if we consider here bracket, notice since cyclic subgroup generated by y also normal subgroup, that means then this would be belongs to cyclic subgroup generated by y. This is also belongs to cyclic subgroup generated by y. That means if we consider this bracket, then this part would be, whole part would be the member of cyclic subgroup generated by y. Then actually this part be the member of cyclic subgroup generated by x intersection cyclic subgroup generated by y. And I have seen this part equal to actually 1. That means this is equal to would be 1. Therefore, from this line we can write it as x to the power a times y to the power b equal to y to the power b times x to the power a. That means any power of x commute with any power of y. And for this relation easily, phi is a homeomorphism. Okay? And since order of domain and codomain is same, then to prove isomorphism, it is enough to show only one. Now we have to prove the kernel is just trivial. Consider x to the power a times y to the power b equal to 1. And since we all of us know the cyclic subgroup generated by x intersection cyclic subgroup generated by y equal to 1, from this line x to the power a and y times y to the power b lies on the intersection, and since this intersection is always 1, so we can write x to the power a equal to y to the power minus b equal to which belongs to cyclic subgroup generated by x intersection cyclic subgroup generated by y. And since this is equal to 1, so we can tell x to the power a equal to y to the power b always equal to 1. That means this map is 1, 1. So there exists always an isomorphism from cyclic subgroup generated by x direct product cyclic subgroup generated by y to z. Therefore we can tell easily G is isomorphic to Z mod 3Z direct product Z mod 2Z, which is always isomorphic to Z mod 6Z. Okay? Well, therefore any group of order 6 upto isomorphism, either G is isomorphic to dihedral group means D3, which is also isomorphic to S3, and this is possible when G is non-cyclic, and when G is cyclic then G is isomorphic to Z mod 2Z direct product Z mod 3Z, and which is similar to Z mod 6Z. Okay, that means up to isomorphism any group of order 6 there exists two group, one cyclic and other non-cyclic. Now let's see group of order 30. As proceeded before, there exist Sylow 2 subgroup, 3 subgroup and 5 subgroup. Here I will do everything quickly. If you calculate, you will see number of Sylow 2 subgroup will be either 1 or 3 or 5 or 15. Similarly, Sylow 3 subgroup equal to either 1 or 10 and Sylow 5 subgroup equal to either 1 or 6. In Sylow 2 subgroup, there exist many possibilities. So, I will see at first Sylow 3 subgroup and Sylow 5 subgroup. If we consider N3 equal to 10 and N5 equal to 6, we always know the different Sylow subgroup always have a trivial intersection. And since N3 is cyclic and different, that means there exist 10 Sylow 3 subgroup whose intersection is only identity. And each Sylow 3 subgroup contain 2 elements of order 3. That means there exists 10 times 2 means 20 elements of order 3. Okay? Well. And now similar argument for Sylow 5 subgroup, I will get 6 times 4 means 24 elements of order 5. And here notice 20 elements and here 24 elements. That means 20 plus 24 and always identity exists, and this is exist from order of the group. So one of them, that means Sylow 3 subgroup or Sylow 5 subgroup, must be normal. Let's consider S is Sylow 3 SSG and K is Sylow 5 subgroup. And since one of them must be normal, so consider S is a normal subgroup. And we know since S is a normal subgroup, then ASK must be subgroup of G. And order of ASK, we all of us know this is order of S times order of K divided by order of S intersection K. And we all of us know this is PQ type group, and since P does not divide Q minus 1, so the group of order 15 obviously will be cyclic. And we all of us know any cyclic group always be normal. So for all G in G, G ASK, G inverse always will be equal to ASK, and this is possible only for the subgroup ASK is normal, and always K is contained in the subgroup ASK. So all conjugate of K, that means G, K, G inverse, will be contained in the subgroup ASK. And since the subgroup ASK is cyclic, and we all of us know any subgroup of a cyclic group is always normal. So all conjugate of K would be only K. Okay? And K is contained in the subgroup ASK. That implies K is always normal subgroup in G. And I have considered S is normal subgroup. Then I have got the subgroup K is also normal. And in similar argument, if you consider K is normal, then S will be also normal. Initially I have seen one of them must be normal, but now I have got both of them must be normal. And this is the deep construction of any group, and this is actual topic of today's lecture. In my earlier video, I have seen construction of non-abelian group using semi-direct product. The theorem is, suppose S and K two arbitrary group and K is a cyclic. Suppose K is generated by X. Suppose there exists two homeomorphism, phi 1, phi 2. From K to automorphism of S. Then assume sigma phi 1 K sigma inverse equal to phi 2 K, where sigma belongs to automorphism of S. Here phi 1 and phi 2 are conjugate to each other. If K equal to infinity, then assume there are 1 function exist. If order of K is finite, then there exists obviously a 1 function. And we can tell then A is semi-direct product K with the homeomorphism phi 1 is isomorphic to A is semi-direct product K with the homeomorphism phi 2. That means if both of them means phi 1 and phi 2 have equal Sylow p subgroup, and if this p subgroup divide the order of the group G, then we will get semi-direct product which is isomorphic to each other. Different choice of automorphism will lead different non-isomorphism group. And if you can to understand this structure, then you will construct any group of any order. As for example, consider group of order PQ where P divides Q minus 1. Then S is obviously isomorphic to Z mod QZ. And automorphism of S equal to Z mod Q minus 1Z. Okay? And this is possible because the group is cyclic. Then there exists unique subgroup of order P in the automorphism of S, because this is the cyclic group. Therefore, by this theorem, we can tell easily Z mod QZ semi-direct product Z mod PZ are same up to isomorphism for a non-trivial homeomorphism phi. And the homeomorphism is look like there exists a homeomorphism phi from Z mod PZ to automorphism Z mod QZ, and this homomorphism is considered as phi. Then image of Z mod PZ under phi will be subgroup of automorphism of Z mod QZ. Okay, and since automorphism Z mod QZ is cyclic, so there exists only unique subgroup of order P. So we can tell G is isomorphic to Z mod PZ semi-direct product Z mod QZ when G is non-abelian. Therefore, up to isomorphism, there exists two group of order PQ. When G is cyclic, then G is isomorphic to Z mod QZ, Z mod PQZ. When G is abelian means cyclic, and when G is non-abelian, then it is isomorphic to Z mod PZ semi-direct product Z mod QZ. Okay? Well, now let's come back our original example group of order 30. Few minutes ago I have said there exists 5 SSG consider this is as Ace, which is isomorphic to Z mod 5Z and 3SSC, which is subgroup of Z, which is isomorphic to Z mod 3Z. Consider also this subgroup generated by X and this subgroup is generated by Y. And earlier you have seen also A's K be the normal subgroup of the group G and R be the Sylow 2SSG, which is isomorphic to Z mod 2Z, and this is also normal subgroup. And consider this subgroup also generated by the element Z, and intersection of these two subgroups H, K and R are prime to each other. So here the two Sylow subgroup is a complement of HK in G. Then HK times R equal to G, and we can tell easily then G is isomorphic to HK semi-direct product R, and since HK is a cyclic, so we can tell also G is isomorphic to H cross H direct product K and semi-direct product with R. Consider there exists a homeomorphism phi from R to automorphism H direct product K, and this homeomorphism denoted as phi. Here R is Z mod 2Z, and we all of us know automorphism of H is Z mod 4Z. That means this direct product Z mod 4Z direct product, here K means Z mod 3Z, that means this automorphism is Z mod 2Z. That means there exists a homeomorphism from Z mod 2Z to Z mod 4Z direct product Z mod 2Z, and now we have to find what is possible homeomorphism. When phi is trivial, then G is isomorphic to Z mod 15Z direct product Z mod 2Z, and which is actually isomorphic to Z mod 30Z. Now let's talk about non-trivial homeomorphism. Since order of 1 in Z mod 2Z is 2 and order of the image phi 1 divides the 2, so here R sends to elements 2 in automorphism H direct product K, and we all of us know the structure of the element of order 2 in automorphism H direct product K. There exists 3 elements of order 2 in Z mod 4Z direct product Z mod 2Z. First possibility is X maps to X, and this is actually the identity automorphism of X, and Y map to Y inverse, and this is inversion automorphism of K. Other possibility is opposite, Y map to Y inverse, here Y, and X maps to X inverse. And third possibility, both map to inversion, that means X map to X inverse and Y map to Y inverse. Now say here G is isomorphic to H direct product K, semi-direct product R means H means here cyclic subgroup generated by X, that means this is equal to cyclic subgroup generated by X, direct product cyclic subgroup generated by Y, semi-direct product cyclic subgroup generated by J. And here notice X maps to X and Y maps to Y inverse. If we change this as cyclic subgroup generated by X direct product cyclic subgroup generated by Y semi-direct product cyclic subgroup generated by Z. And here notice semi-direct product. That means there exists a non-trivial homomorphism from Y to Z. And this is actually isomorphic to Z mod 5Z direct product. Notice this structure. This structure we all of us know is similar to D3 group, dihedral group of order 6. And if we consider a second case, here H direct product K, similar to, we can write it as K direct product H. That means we can write it as cyclic subgroup generated by Y direct product. This is cyclic subgroup. For this cyclic subgroup generated by X semi-direct product cyclic subgroup generated by Z. And cyclic subgroup generated by Y means Z mod 3Z. And this structure is similar to dihedral group of order 10. That means this is isomorphic to Z mod 3Z direct product D5. And for third case, there is an inversion in the group H direct product K, which is cyclic group and whose order is 15. That means for third case, this is isomorphic to Z mod 15Z, and there exists a non-trivial homomorphism from H direct product K to R. That means this is semi-direct product Z mod 2Z, and which is, this structure is similar to dihedral group of order 30. That means there are exactly 4 isomorphic type group of order 30, and one of them abelian and other be non-abelian group upto isomorphism.